It's my pleasure to welcome Mikael Witte today. Mikael is a ASP postdoc. He started just shy of 1 year ago. He finished his PhD at the University of California at Santa Cruz last year under Patrick Chuang with the topic of collision coalescence in marine stratocumulus. And here basically continues that broad field. The research topic generally is improving the representation of clouds in numerical models using in situ aircraft observations and large eddy simulations. I was quite surprised. You just had your second first author paper out, right, a couple months ago. So keep going on that. It's really good. And today's title is Scaling Analysis of Cloud and Rain Liquid Water Content and Implications for Microphysical Parameterizations. With that, I pass on to Mikael, please.
Thank you, Holger. So thanks for the introduction. I'd like to start out, acknowledge my co-authors on this, Hugh Morrison, Jan Jensen, Aaron Banzmer, and Andrew Gettleman. And let's dive in. So in numerical models of the atmosphere, we would like to be able to represent clouds. This is an important thing to do. So there are lots of different kind of scales of models that we have. And most importantly, I want to point out that we can only do explicit microphysics at the very smallest scales. Every larger scale model than that, starting with cloud scale like LES, going all the way up to GCMs, we're essentially operating on populations of drops. And implicit in this is that within any grid box, we are making an assumption that whatever is in that grid box locally matters. So microphysics is a local process, no matter what the scale of your grid box is, whether it's 50 meters in an LES or 100 kilometers in a GCM. So this might be problematic because drops in a GCM that are 50 to 100 kilometers apart from each other probably aren't interacting. So to show how this results in problems, we'll start out with this equation up here on the right side. This is just an equation for the autoconversion process, which is how we make raindrops using a very simple parameterization. And this increase in rainwater amount, which is the derivative on the left side, is going to be equal to this nonlinear equation on the right-hand side. So the Q's here throughout the talk are going to refer to species water content. The brackets will denote a grid mean value. And for the subscripts, cloud will be small drops, rain will be big drops. Beyond that, it doesn't really matter what the specifics are. We just want to be able to separate these out. And what we see here is that we drive this equation forward by using grid mean values. But we have a problem. And that problem is that the process rate we get from using a grid mean value is not equal to the mean process rate we would get from integrating over a number of local values. So people realized that we got process rates that were way too low, especially in GCMs, and the way that this was handled early on was just by applying arbitrary tuning parameters. And these arbitrary tuning parameters would be used to optimize something like outgoing long wave radiation or surface precipitation, or maybe they were tuned to observations of what the auto conversion rate would be, but they were generally ad hoc. So as we moved forward, we started to realize, well, okay, if we know the distribution of values of some field within a grid box, and we can express that with something simple like a Gaussian or a log normal or gamma distribution, then we can integrate over that probability density function, and we can come up with an accurate process rate. And so now we have got to what we call upscaling schemes. So saying we have this local distribution of Q, of water content, and we give that an accurate PDF, and we can get the process rate right. But is liquid water Gaussian? So this is 500 hertz liquid water content from a single 60 kilometer leg. We can see that it's very spiky. It varies a lot over very small scales. And we have highs and lows, local minima. We take this, we turn it into essentially a histogram or a PDF. And what we can see is, okay, Maybe it's Gaussian-ish. It's got a long left tail. We can maybe use a mixture of normal distributions, but is this what we see here at a 60 kilometer scale relevant to what's happening at a local scale? Is it relevant to the physics? Now this is basically what leads us to what we're going to discuss in this talk. So we have 3 questions that we're going to examine with varying degrees of depth. The first is, if we look at this PDF, is it the same shape if we vary either the grain size or sampling frequency? Is it the same if we use 500 hertz versus 1 hertz? Or if we change the averaging length, whether we're looking at a 10 kilometer leg or a 60 kilometer leg? Furthermore, how do different PDFs of fields that we care about covary or interact? And finally, this is kind of the most fundamental question to me, is what, if any, are relevant length scales for microphysical processes? So let's actually start out with the middle question here of how do PDFs covary, and why would we care about this? So let's look at another process rate here. Now we'll go from auto conversion to accretion, where we again have a nonlinear process that depends on cloud liquid water and rain liquid water. If instead of just operating on the means, we introduce the PDFs of QC and QR, and I'm not saying what the shape of those PDFs necessarily is, we get the equation below. And this is out of the Morrison-Gelman 2008 parameterization. So essentially we still have this dependence on the grid mean values, but we now also introduce this enhancement factor E. And this is going to depend on the specific distributions of QC and QR that we use, as well as the correlation between QC and QR, this factor rho. Now rho can only vary between 0 and 1, so you may be thinking, how can this exert such a large effect on the process rate? But if we assume, say, log normal distributions of the underlying fields, it actually depends on e to the correlation. So it can exert quite a large effect. So quantifying this rho is what I'm going to spend most of the talk doing. People have done this from satellite observations and large eddy simulations before, but they either have not been able to get down to very small scales, which is the case with remote sensing, or they're done with the same imperfect microphysics applied to populations of drops that we saw in large eddy simulations. So going forward, I'd like to introduce the observations that I'm going to be analyzing and how I'm going to use them. We'll do some spectral analysis to talk about scale invariance and how from this scaling behavior we can then say something about what this correlation between different fields should look like, in particular cloud and rainwater. And then finally I want to talk about a framework from which I hope in the future to start developing a kind of structure-aware parameterization of microphysics. All right, so the observations we'll be using are C-130 observations from the Vocals campaign. This took place off the coast of Chile during fall of 2008. And I'm going to be using the highest possible data rate we can get from the C-130, 500 hertz, for the analyses that'll follow here. And the 2 instruments we'll be using are the Gerber PVM100A. This is basically just going to be measuring cloud drops. It measures drops 3 to 40 microns in diameter. And it's an analog instrument, which means it could ostensibly be run at even higher rates. And for drizzle or rainwater, we'll be using a 2-dimensional cloud probe. And this measures drops 25 microns to 1.5 millimeters in diameter, 64 linear bins. The star is just to remind me that we throw out the smallest drops here, 25 micron to 50 micron drops, because there are a lot of issues with the optics of those. So given a mean true airspeed or aircraft velocity of 110 meters per second, this 500 hertz sampling rate, it corresponds to a spatial scale of about 22 centimeters. So that's the smallest scale we can get down to here. And we're going to hope that maybe this is a scale that would be relevant to the physics that we're trying to describe. And then we're only going to analyze long level in-cloud legs with leg lengths ranging from 30 to 120 kilometers. So we are going from this 22 centimeter sampling length or grain size all the way up to over 100 kilometers leg length, which is going to be relevant to GCMs or large scale models. Just to give you an idea of what these flights look like, here I've got plotted the C-130 flight track taking off from Arica here, going out. The color is the aircraft altitude. And you can see most of what ends up happening is we do these long level legs and then fly back above the cloud. And basically we're just trying to hit this extensive stratocumulus deck here. In time series here of the same flight, we can see I've got 3 panels here. The top is the aircraft altitude, middle panel is cloud liquid water content, and the bottom panel is rain liquid water content. What I've done is highlighted in red the segments that I'm analyzing from this flight. And what we can see immediately here is that while there's often pretty reliably high liquid water content in any of these long legs, the relationship with rainwater is quite variable. Where in some cases we seem to track pretty closely, but in others there's almost nothing. So this is going to tell us right off the bat that there is not a constant relationship in terms of covariance of QC and QR. And up here I'm only showing you the 1 Hertz time series, and I'm doing that just because if I showed you 500 Hertz it would be an absolute mess visually. So this raises a question though. So I have this 500 Hertz data set that we could use, but most people would just use what you get off the ELL website, the 1 Hertz data set. So how do we choose a sampling frequency? What I'm showing here are PDFs of cloud liquid water on the top line and rainwater on the bottom row at various different sampling frequencies. Starting at the highest over here on the left, if we just look at the top row, we can see that as we go to increasingly coarse sampling, the shape of the PDF is fairly constant. It doesn't change very much. Maybe it gets a little bit less continuous, a little bit jumpier or spikier here at the lowest frequency, but overall the shape is fairly well defined no matter what. Whereas for rainwater, on the other hand, we can see that at 500 Hertz, we're clearly not sampling the PDF very well. What we end up getting is these kind of discrete spikes here, which is essentially from seeing single drops. So we're kind of forced to go to a lower sampling frequency here simply because the sample volume of the 2DC is small enough such that we can't sufficiently sample it at these really high rates. Now I don't know what the exact metric is for an adequate sampling here. Is it whatever defines the smoothest PDF, which we would say is probably this 100 Hertz rate, or is it something different, a convergence of shape maybe, so something in the 20 Hertz or 5 Hertz range. And finally, I just want to point out that here we get a very kind of spiky PDF at the lowest rate. It's fairly discontinuous, and we'll come back to this point later in the context of intermittency. So I'm not making any statements about how you should use this, but if you are doing analysis of it, you probably shouldn't just use the 500 Hertz sample rate. Okay, so let's jump into some spectral analysis. So the main tool we're going to be using here is the power spectral density. And this can be used in a number of different ways. So for some processes, they'll display peaks in variance or power at characteristic scales or frequencies, such as in this left panel, we've got well-known interglacial frequency bumps in terms of temperature and oxygen isotopes. But many other processes, on the other hand, don't really have a characteristic scale at all, like turbulence, for example. So we call these processes scale invariant in this range that's in the black box here, because their variability is a power law function of scale. And these do not necessarily obey Gaussian statistics. And this is an important point for us if we want to be able to parameterize PDFs in terms of these really easy, analytically tractable distributions. So how will we do this? How will we apply this to liquid water content? Well, here's our single 60-kilometer leg again. What we'll do is we'll say, first of all, that any segment that we're going to analyze, we want at least 60% of it to have greater than some threshold liquid water content for cloud water. And for rainwater, we'll relax that threshold a little bit simply because it's so much sparser in space. And then we'll subdivide into a number of subsegments. And the reason for this is as follows. So here we've got a power spectral density, or the power spectrum for this leg that I'm showing. I've subdivided it into 4 15-kilometer segments for 2 reasons. One is that if we want to have confidence about what's happening at these large length scales, we need to have a number of different realizations. So instead of just having one 15-kilometer point, we'd like to have 4. And the other is that, as we can see out here in this just mess of color, the spectrum gets really noisy. So we've subdivided into segments, and the other thing we're going to do is bin by frequency. I think I say octave bins on here, but these are actually half-octave bins. But what ends up emerging as we aggregate over both length and frequency is that we get something looking like a straight line here, this Markov scale invariance that we'd like to see. Now, I'm not the first person who's ever done this. In the past, and a paper that's coming out very soon, everyone who's looked at liquid water content from aircraft observations has found what we call a scale break. So that's what these red arrows are pointing to, where we get a deviation from the scaling behavior that we see in the scaling regime here. So pretty much all of these come from 2 different papers, and they all find a scale break somewhere between about 2 and 8 meters. So I just want you to keep this in mind as we talk about about our observations. So coming into our results now, here are the aggregated PSDs from vocals for each of the 12 research flights I could get 500 hertz data for. And the coloring of these curves doesn't matter. All I want you to note is that they all scale in approximately the same way. They deviate a little bit from this -5/3 line, which is what we would expect if they were just passive scalars in turbulence. And maybe there are a couple flights that look like they might have a little bit of a scale break, and that's what I've done for the dashed curves. But these are still not nearly as pronounced as these past studies. So in this range that we would expect to see a scale break, there's nothing. And instead, we get this sharp drop off at about 200 hertz. So why aren't we seeing a scale break at this 2 to 8 meter range and instead seeing a drop off? Well, let's simplify a little bit. Now this is the aggregate over the entire field campaign of 500 hertz cloud liquid water content. And we can see where these red arrows are, a scaling range from 56 centimeters to about 14.5 kilometers with a spectral slope of -1.38. Now again, if it were turbulent, we would expect it to be -5/3 or -1.66. But we're close, and we actually expect a slight shallowing of this power spectrum because cloud drops have inertia. They're not just passive tracers. And it's been shown in DNS studies that as you increase the inertia or the mass of the drops, or the Stokes number, if you will, that you see a flattening of this spectral slope. So what's different? Signal processing is essentially what it comes down to. On the C130, we oversample the instrument at 10 kilohertz. And basically what this allows us to do is reduce analog to digital noise. And this first step, this is the key. This is what most other people or most other aircraft facilities aren't doing. So my hypothesis is that essentially this 2 to 8 meter scale break is actually just analog to digital noise that has not been filtered out. So we filter the signal down to 500 hertz, and then you get down to lower just by simply averaging in time. But the point being that we're seeing something that nobody else has, and it's not as if there is some physical explanation for a scale break to essentially white noise. It's actually just a signal processing problem. So now what happens if we add rainwater? Well, now we do see a scale break, and a pretty significant scale break at about 62 meters. So is that to say that the point I just made about signal processing invalidates myself? No. So what we end up seeing here is that, like I said, liquid water content, or the rain liquid water content, is very sparse in space. You're seeing very few drops, especially when you're looking at the 500 hertz observations. So what this figure here from Gerber 2001 shows is that as the drop number concentration is decreased, we basically end up seeing this flattening to this flat slope, which is just white noise. So again, this is essentially a statistical issue as opposed to a physical issue. All it means is that essentially the instrument doesn't see a high enough density of drops for us to be able to get information about what's happening in these smaller sizes here. Okay, so both of these quantities are scale invariant, but this still doesn't tell us how they interact. So to get at that, we'll do co-spectral analysis. It's the same idea as the PSDs I was just showing you, but now we're going to analyze the relationship of both time series, cloud and rainwater, as a function of frequency. Basically, this is just the Fourier transform of the cross-correlation function. We'll only use the real part of the resulting cross-spectrum, the co-spectrum, which is equivalent to the covariance at a particular length or frequency. So here's the co-spectrum of vocals average 100 hertz, cloud and rainwater, which I've filtered it down to 100 hertz just so I can have confidence that we're not just seeing white noise in the QR signal. And what we see here is, again, a roughly scale invariant spectrum. So this is interesting because now we've established that this covariance does seem to have some relationship with length scale. So if we recall that if we integrate over a PSD, we basically get the variance of a function. It's the same thing for the co-spectrum. We can get out the covariance by integrating up that co-spectrum. And then we can get the correlation, rho. So we don't expect a constant covariance with length scale, which is what a lot of people have applied in the past, especially from the parameterization side of things. But since the co-spectrum is scale invariant, maybe we can analytically predict correlation at any given length scale. So let's test this out. Let's just apply this. We'll just look at correlation at different averaging lengths from a particular vocals flight. So here's RF13, the same flight I've been using as an example. Along here, the coloring of the different curves has no meaning. It's just to differentiate among the different legs. And we can see that there's a fairly complex relationship here. Generally, what we can say about this is that at the smallest length scales, there's the lowest correlation, and it tends to increase with length scale with a little bit of noise. And in some cases, we kind of have a drop off at the very largest length scales. And I don't know if that's noise or if that's physical or what the case may be. So if we were just to look at this, we might say, it's not very easy to say anything about this. How can we actually parameterize this? But if we look at all the vocals legs, and then we arrange them, or we color code them essentially by the cloud drop number concentration, we start to see a pattern emerging here, where the lowest drop concentration legs tend to have very large correlations, and the highest concentration legs have the lowest correlations. As you can see, there's still a good number of these dark blue low concentration points with almost no correlation. So while it would be really, really tempting to just say, okay, well, we'll just use this figure and plug in a parameterization into CAM from here, it's not quite that easy. There's clearly some other things controlling this. But to first order, I think we can say with confidence that what controls the correlation of cloud and rainwater would be the drop number concentration. So let's review so far. We've established that cloud and rainwater are scale invariant. For cloud liquid water, from about 50 centimeters to 15 kilometers. And we don't see a 2 to 8 meter scale break here, which we think is likely because of reduced analog to digital noise. So basically signal processing choices that are different from aircraft to aircraft. For rain liquid water, on the other hand, it's a much larger low scale break from 62 meters all the way up to 30 kilometers. And here we can't get at these smaller scales to say anything about scale invariance because we simply don't have an instrument with a sufficient sampling volume to assess that. We've also established that the correlation between QC and QR is scale invariant, and the co-spectrum tells us from a theoretical perspective why we would expect this. And finally, we were making progress towards parameterizing the correlation as a function of both length scale and cloud drop number concentration. But is correlation sufficient? Now I bring this question up and I put these two PDFs here because because I want to come back to something I said at the very beginning, is that we can define these PDFs over some large length scale, 60 kilometers. But is this what's relevant to the physics? What we're assuming is that any point on this Cloudwater PDF can interact with any point on this QR PDF. But physically speaking, we just don't expect drops that are tens of kilometers apart, or effectively, or realistically, probably hundreds of meters apart, to interact on any reasonable timescale for which you're trying to figure out physics. Fortunately, we have some tools that can tell us about structure and organization. And for this, we're going to turn to the fanciest log-log curve fitting tool you've ever seen, bifractal analysis. So bifractal analysis is a tool that allows us to characterize a field by just two different numbers. One of them is called H1, and essentially what we're getting at is how smoothly does our field vary? How rough is it? I mean, to put it in geometric terms, how rough is it? To put it in statistical terms, to what degree is it statistically non-stationary? And the other criterion is C1, or how spiky is our field? And this is getting at how intermittent is it, or to what extent does it exhibit singularities? And we can only apply this to fields with a spectral slope between 1 and 3. So this is important. This was the original motivation for doing all this spectral analysis in the first place, was just to establish that cloud and rainwater are in this range of spectral slopes to which we can apply this analysis, which, and then this number, the spectral slope in this range, basically indicates a non-stationary field with stationary increments. So to give you an idea of what this actually means, I copied some figures from a paper from Sasha Marshak. On the left side, we have H1, and what I'm showing here is just, as we increase this, we see kind of what this means geometrically. So for H1 equals 0, we've got essentially Gaussian noise. It's just a random step. As we get to higher and higher values of H1, we start to see less kind of action at the smallest scales and a gradual smoothing until we get to H1 equals 1, which is just describing a continuous function. For C1, on the other hand, as we go from top to bottom, again, we're going to be increasing intermittency. And then you'll also notice this little max over mean. As C1 approaches 1, the max over mean will approach infinity. So that's what we mean in terms of how this is a singularity. So what we can see here is that for 0, we've basically got no spikes, no activity. This could actually probably be equally applied to H1 here. Where is my mouse? Where we've basically got the max is fairly close to the mean. This would be a very non-intermittent case. And as we go down, we start to see, and this is where I'm saying spikiness is what we're measuring here. We start to see that the spikes really start to dominate the entire signal. And so as we get more intermittent, we see just a very small number of events starting to dominate everything that we're seeing. In practice, what does this mean? So in terms of some past results, here's a figure from Davis et al. 1999, where we can see, this is the bifractal plane here. We've got H1 and C1 both ranging from 0 to 1. And on the axes, there are some kind of common functions to give you a little baseline for what these things mean. Where at the origin, we've just got something like stationary Gaussian noise, white noise, pink noise, you name it. As we go out along the H1 axis here, we basically go through additive cascade models here. So we can do fractional Brownian motion, all the way out to 0.50 here. This would be just standard Brownian motion. And as we get all the way out to 1, as I pointed out before, we get to essentially differentiable functions. Oops. For C1, on the other hand, as we go up, now we're looking at multiplicative cascade models. And the most extreme version of this would just be a Dirac delta, right? You have one point that's carrying the entirety of the signal. So the max over the mean, again, approaches infinity. Now to go to the kind of combined extreme, we get to a Heaviside step function where we have all one value, all another value. And then almost all of atmospheric science falls in the middle. So this gray shaded area is just showing what we would expect for passive scalars and turbulence, turbulent velocity, anything that has no mass. And then surrounding it, these other points are some past results. And what we can see here is that for all of the liquid water content observations, they've ended up falling really close to what we would expect from turbulence. And this makes sense. Small drops don't have that much inertia, so they shouldn't deviate that much. For a liquid water path, we get a little bit different, a remotely sensed liquid water path, we get a little bit different characteristics, which I have not actually seen a satisfactory explanation of yet. But in any case, we kind of see all of these cloud liquid water observations falling close to turbulence. So this is all well and good, but how do we actually get to these numbers? Well, what we're going to do is we're going to use structure functions, and what these do is they now tell us about variability from a 2-point perspective, whereas the spectral analysis from before was a 1-point perspective. It's just counting up how many of something happens and turn it into a histogram. So now we're actually looking at the relationship of every point to all its surrounding neighbors. And that's what this first equation is showing. So since we know that our field is scale invariant and in this range of spectral slopes that allows us to apply the analysis, then the qth order structure function should also scale. So now if we take the average over all of the points in our time series or in our field, they should scale with this family of values zeta q. And then we can get to quantifying the roughness or non-stationarity with the Hurst exponent, which is just the scaling exponent of the first order structure function. And like I said, this is the fanciest log-log curve fitting exercise you've ever seen. So here are structure functions of 5 different orders ranging from 1 to 5. The x-axis, this KL, is essentially, you can think of this as the log base 2 of the number of points that go into it. So we're going all the way out to 2 to the 15 points, which is the segment length that we're using. And then we're just fitting curves here. And what we find is that this is Volko's average cloud liquid water content, we get an H1 of 0.24. Good, not too difficult. To get the intermittency measure, on the other hand, we will normalize the structure function, coarse grain it, and it should also scale. So what coarse graining means is that now we are going to vary the actual grain that we're looking at. We're going to look at the gradient field at increasingly long length scales to see how this, to see the extent to which one point or some very intensely active parts of the signal come to dominate everything. Now here we have another added little wrinkle in that the k the exponent for order 1 is always 0 because we've normalized this. And so if you're just looking at the first order of a normalized function, it should just be it should be 0. So now we need to actually estimate C1 from the derivative of this family of exponents k. So here again are the normalized structure functions on the left panel for all of vocals for a couple different orders, and this is small because it's not so important that you see this. I would like to point out that the assumption of a linear relationship starts to get dicey very quickly. But fortunately for us, we really only care about what's happening in the vicinity of q equals 1. So what we have here then on the bottom right panel, and I know the numbers are small, but that's because it doesn't really matter what the actual values are, is that we can see how this family of exponents kq briefly goes less than 0 for q between 0 and 1, and then increases very quickly at higher orders. And we're just estimating C1 as the local derivative at q equals 1, and here we get a value of 0.07. So we've done all our fancy curve fitting. Let's see how things look for the rest of vocals beyond just the average. So now we've come back to the bifractal plane, and what we've got here are, I'd like to show that the effect of aggregating here and how noisy these properties are. So the blue markers here are individual legs. And here I've used 15 kilometer, or no, these are aggregated legs, so combining all of the subsegments. The subsegments are so noisy it wasn't worth showing them. And what we can see is that with respect to these green stars, which are results from past studies, the individual legs span a wide range of values. I mean, they all kind of are consistent with what other people have found, but they're pretty variable. As we then aggregate all of these legs by flight, we see a nice clustering where we start to get closer, or we start to converge to a single value. And then this black diamond here is the average for all of vocals. And this is this 0.24, 0.07 that I was showing in the past couple figures where I was detailing the method here. What's nice is that we fall right in line with what other people have found before. And basically this has been interpreted as meaning that whatever is setting the spatial distribution or spatiotemporal distribution of cloud liquid water is essentially universal. That's good because it means that we can operate on one of these fields and have an expectation that it should be the same no matter what the meteorological conditions are. If we go to rain liquid water content, we see a very different picture. I'm gonna do a manual auto animation and just flip back and forth between these two for a second. Whereas cloud liquid water clusters really nicely, rain liquid water is kind of all over the map. Now this is due probably for a couple of reasons. One is just that these signals are a lot noisier. Another is that maybe we are kind of seeing some combinations of physical regimes, closed cell versus open cell stratocumulus, high drop concentrations where there's very little rainwater to begin with, etc. But as we go and aggregate from individual legs to flights, we don't see that much convergence. It's not really until we look at the full vocals average, which is probably looking at 2 to the 15 times 13 points. So we're looking at many millions of points here to be able to get an actual signal out of this. And again, though, we're confident in this result because we're agreeing decently with the past results that other people have shown. So now we can just look at that vocals averages versus the past results, and we can start to think about what does this mean for actually starting to put together some sort of structure-aware parameterization. So here we can see that these past results, and I'll just go kind of through these one by one. So here we've got liquid water path again, and like I said, I think this is to the right of turbulence for reasons that I don't understand. It could be that it's vertically integrated. It could be in terms of what the drop size response is of a microwave radiometer. I'm not exactly sure. But these other 4 cloud liquid water points are all specifically looking at liquid water content from aircraft observations, and SOCEX, ASTEX, and POST are all using the same instrument that I'm using, although at different sampling frequencies. So it's interesting to me that there is some variability here. I think that what other people have ascribed as kind of these universal characteristics, I would call roughly universal. And I don't know if this is a consequence of signal processing or different meteorological regimes, which they've tried to downplay. Especially, I think this SOCEX point deserves a little extra attention because this was in a much more complicated regime than all these others, which we're just looking at straight marine stratocumulus. On the other hand, then, when we look at kind of the rain, yeah, done.
What's the lowercase m equals 1?
You know what? I copied it from another figure, and I don't know. I should have just removed it. So I'm not gonna speculate because I didn't look into it. They also, so in the figure I took that little shaded area from, they also had an m equals 2, which sat up here. So my guess would be that it was I'm not going to guess. There's no point in that. All right, where was I? Okay, so for rainwater, on the other hand, I actually don't really have another apples to apples comparison to make. So I'm looking at liquid water content directly, whereas other people, this actually all comes from Rob Wood's paper on horizontal variability in precipitation, and he looked at rain rate, which is a higher order moment than liquid water content. And so perhaps we would expect, if we're looking at a higher order moment of the drop size distribution, that we should get a more intermittent result. Because essentially, these larger drops, which should be sparser and more occurring more intermittently in space, will start to dominate this intermittency signal. And I think that also explains why this radar point, which is the most intermittent of anything on here, and is an even higher order moment than rain rate, should be highest up in terms of intermittency. But if we back up and we say, well, we could probably draw a line through the middle here and say that cloud water falls on one side of things and rainwater falls on the other, then yeah, we can say this is more or less universal. So maybe then we could generate synthetic fields to understand and reproduce the structure of precipitation without having to rely on a dynamical model. I think this is a really powerful point that actually kind of skirts around having to get the actual microphysics down really well. And so this is kind of the direction I'd like to go next, but there's a lot of complicated math to actually simulate fields within this framework. All right, so from here I'll start to wrap it up. So cloud and rainwater are both scale invariant across a wide range of scales. We don't see scale breaks in our cloud water because of signal processing. We can't get at the small scales in rain liquid water because of small sampling volume. So if anybody has a brilliant idea of a better way to observe drizzle than this, I would love to hear it. That can actually get down to these small scales too. That's where radar doesn't work because the footprint or the beam width by the time it actually hits cloud is still going to be a minimum of tens of meters. We can also parameterize the covariance or correlation of rain and liquid water or cloud liquid water as a function of length scale and cloud drop number concentration. And we have a good theoretical basis for this. So even if we were just to look at individual spectra, co-spectra rather, and categorize them by their drop concentration, we can probably come up with a pretty clean parameterization there. And finally, the near universal bifractal characteristics of cloud and rain liquid water, I think can give us a framework for understanding and reproducing the spatial structure of precipitation, which I think, like I said, is a really powerful concept because it might get us around actually having to get microphysics physically relevant on a GCM scale. So with that, I will take any questions. Thank you.
Questions?
Yeah, I missed the definitions of C1 and H1. Could you go over that a little bit?
Let me back up here.
Yeah.
So H1 is telling you about statistical stationarity or the lack thereof.
Yeah, but what is, do you have a defining equation or something like that?
Yeah. So here, we're just getting H1 from the first order structure function.
Oh, yeah, okay.
So this blue line up here at the top, I just do a nice log-log fit to that.
Okay.
And then for C1, we're looking at the derivative at q equals 1. And the specifics here are not super important, but the point is that because the value of K1 is 0, we're going to use L'Hopital's rule, look at the derivative, and that'll get us the value that we're interested in. And this approach is pretty, it comes from Lovejoy and Schertzer. And it's been applied to a lot of different things, to water vapor fields, aircraft measurements, ocean
Where did you say
currents.
it came from?
Lovejoy in Schertzer.
Oh, okay.
Yeah. So I mean, this comes all of this comes out of their, I think, 1987 paper.
Could you go to your third last figure?
Third last figure.
Something, maybe second last or third last.
This
keep
one?
going, keep going.
Keep going.
Up till in your conclusion. Yeah, this one here.
Yeah.
Okay. So I really like the fact that you're having a length scale and you're having correlations. And I think in this case, it was between QC and QR, right? And that therefore, within a certain grid point, you should be able to get a higher accretion rate if you were doing Karatnow and Kogan and so on.
Yeah.
And that's all good and fine. But if you're having a correlation coefficient of 0.3, how much faster is the rate then within a grid point?
Well, it depends. It depends on the underlying distributions that you're assuming. Like I said, if you assume log normal distributions, which Hugh, is that what you guys do gamma, right? I think Vince Larson, who basically took kind of the club approach and then tried to add microphysics to it, just assumed log normals. And in their equation from it, I know that the enhancement factor ends up depending on the exponential of rho. So you can end up getting a pretty significant contribution to the enhancement from that correlation.
But you don't want to give us any numbers?
I don't want to give you any numbers, and the reason for that is because of how, I looked at it, but there's so much blue down in here that you can't see that I just tried to do like 50 per cc bins, and you end up getting too much scatter in what the slopes of each of those fits look like. So it's not clean yet. So there's got to be some other dimensionality to it that I haven't considered.
So hi, Michael. Good piece of work. I really liked how you presented it too. Along with this figure, one comment about this figure before another just mention of one other topic. So in this figure, do you think the really low correlations are coming because some of these high droplet concentrations just aren't drizzling or hardly drizzling?
Oh, and I think that's exactly it, which seems really obvious,
Okay.
but nobody's shown it yet.
I guess I'm just confirming because that's what I think it is.
Oh, no, I would agree with you
reasonable.
completely. I mean, that's kind of that's a little bit of what I assume some of, like I was saying, this mess of blue dots down here is that for whatever reason, I'm just not seeing drops in the instrument. Maybe it's because the boundary layer is really thin, or the cloud layer is really thin.
Yeah.
So I'm not sure exactly what that is yet.
And then just a comment, my only concern that when you try to wrap this up into something that affects stuff that you and I do all the time with microphysics development, parameterization development is, this is great for a stratocumulus cloud. How do you know how it compares to a continental cumulus deep convective cloud and a supercell and every other cloud that's in a numerical model?
Well, I think that's exactly the point. And it occurs, I mean, I think it would be really cool to go out and look at this in terms of mixed phase stuff. But you think that, if I think that a 60 meter scale break is bad, if you're looking at ice particles, I think it would be even worse. So the applicability of this right now is just to warm rain. And stratocumulus, I mean, the reason it's an obvious choice for this is because where else are you going to find 100 kilometers straight of cloud, right? So I agree with you that this is not universally applicable yet, but I will say, like, so in Vince Larson's paper where he goes through his derivation of how you do accretion in terms of probabilities, I'm actually going to go back to the real figure here so I can show you. So they do one LES case, DICOMS 2RFO2, and they find the correlation of extended liquid water and QR, and it's 0.242 in their simulation. And that simulation is on a 6.4 by 6.4 kilometer grid. So let's find 0.242. Let's see, 2, 3, 4, 5, 6. So right about there. And the drop concentration for that case is about 55 per cc. So I think they have a right answer, but it's not the general right answer. So I think at least in terms of how people are using this in these simplified cases where you're just looking at warm rain, really what I'd like to contribute is expanding it from just having this single number on it to at least be able to say, depending on what your grid size is, you can come up with something that is relevant.
So, Michael, very nice talk. Can you go to the bifractor, whatever that diagram? You mentioned at one point that maybe later, the one with some results. You said the one point that on the right-hand side of the turbulence are hard to interpret, but I think it's not that difficult if you, I don't know if that's ice or any mixed phase being involved.
This is all
just
all
liquid?
warm phase.
Yeah, because
Liquid
you
phase.
showed one actually previously in that diagram with the ice. So I thought, sorry, if this is liquid, then it's harder because I think the larger particles might not be actually impacted by the smaller scale turbulence that obviously. So you probably still have a very uniform or stationary kind of a distribution, even with some intensity of the turbulence. But if you said it's all pure liquid, then there may be something else going on.
Yeah.
Yeah.
Very nice, Michael. I had a few questions around the rain.
Yeah.
Q sub r. Raindrops fall, and they don't follow the air motions nearly as much as the cloud drops. So if we go back to the figure that we've been discussing quite a bit, the correlation and yes. So when you see blue dots with low linear correlation rho, is that simply because drops have fallen into that volume? They haven't been produced locally.
That's a really good point. And I mean, full disclosure, I'm not controlling I don't control at all in these level legs that I've chosen where they are in the cloud. So I can see how if you're closer to cloud base,
Yes.
you would expect that there should not be a correlation because those raindrops were not made there.
That's right.
They're coming from a lot higher up.
And
That's a good point.
That's a more general point I wanted to raise, and that is that, if you think of how rain is formed, I like to think of it as a parcel where you've got drops that have certain histories through that cloud, and they encounter liquid water contents as a function of their time through that particular cloud. And so, if you're looking just at the initiation of the rain, it might be different, but if you're looking at a more mature rain situation, I think things become particularly difficult. Because of the sort of, you're looking at a snapshot, and that, it's a sort of Markovian versus non-Markovian aspect of the system.
Right.
So I think that's worth considering, and that made me also wonder, and I'll let you answer, also made me wonder about the, you said that when your drops don't follow the turbulent motions, you expect a shallower slope in the power spectral analysis. That didn't seem to show up in your Q sub r analysis.
Yeah.
It looked very similar.
I have some doubts still about what I'm getting for the 2DC. I think I have done this in a couple of different ways, playing with just kind of how I conduct the analysis. And I have gotten slopes as shallow as, it always changes in the 2DC. The cloud liquid water scaling is always the same. It doesn't matter what you do to it. It's really robust. But for the 2DC, I've gotten numbers as low as 1.09 and numbers as high as, this is about the highest. So I think that there's still a little bit to look at in terms of how robust that result is and how sensitive it is to where you say the scaling regime starts or stops. And also on the sampling frequency. So I'm showing 100 hertz. So basically, the minimum that I could actually get a continuous PDF for. I think that really what I should be doing is it's probably more like 20 to 25 hertz. I mean, that's where I'm saying I would really love to talk to someone who has experience in how you actually determine where you have something that, I guess, a significant PDF to it. I mean, I don't know. I don't know what's the best thing to use here. All I know is that this is clearly not good at 500 hertz. So that's worth looking at. But I want to come back to your point on the correlation. I think, to me, well, for one, like I said, I think that correlation is insufficient. And precisely the fact that you're getting this snapshot is really important to keep in mind. There's a paper coming out from Malinowski's group, which that post data point came from, that looks at the vertical structure. And they do find some pretty coherent changes in how cloud water looks, but they didn't look at drizzle or rainwater at all. So I think that's kind of where this idea of using something to get around having to do the microphysics might be a better solution than try and jam a square peg into a round hole. You know, it's almost, I think it's getting close to this kind of neural network idea of let some framework learn the data and then tell us what we should see instead of trying to do it from first principles. Yeah.
Very, very nice talk.
Thank you.
I'm learning stuff. I have a question about time dependence. I know in some cases certain clouds don't rain at all.
Yeah.
Or if they do rain, they take a long time if they don't evaporate first. And so there's a time dependence that's dependent on the size of the liquid water droplets and the number concentration. So how does that sort of factor into this analysis? Because it seems like these are time-dependent phenomenon, and I don't see time as a variable here.
No, it's not, and that's a very good point. So I've essentially said, let's use Taylor's frozen turbulence hypothesis and just say space is time and just throw it all out, right? But for one, we're not observing some coherent parcel evolving in time. We're flying fast enough that we're always seeing something different. In the large scale, these stratocumulus decks are not evolving so fast. I think that looking at a 30-kilometer leg, which is, like 5 minutes of flight time, you're not going to be seeing huge evolution, especially in stratocu, which are so dynamically weak. So my thought was more, if we throw enough data at this, we're basically just smearing out any time dependence that you would get. So we're using all of these flights from different days, and basically, if there were some regime dependence, I would expect there to be a lot more variability in what's happening on a flight-by-flight basis. So the time part, I think, at least in this context, doesn't matter.
Okay, I would like to thank Michael one last time. He sits over at M-Cubed. If you have any more questions, just go and talk to him. And thanks for attending, and thanks, Michael.
Thank you.